In this video, we are going to learn about normal approximation for binomial and Poisson distribution. Okay, so still remember the binomial and Poisson distribution. So notice that these two distributions are the discrete probability distribution. So in this topic, we are going to use the normal approximation to approximate the binomial and Poisson distribution. So why do we have to use the normal approximation? Because we want to approximate the probabilities of random variables where we don't know all of the values because we have limitation. Okay, the table have limitation. Okay, and sometimes the problems needs more than the value from the table. Okay, or for a very large range of a potential values where it would be very difficult and also time consuming. So that's why we will learn about normal approximation for these two distribution. Alright, before we move further on the normal approximation for binomial and also Poisson, you need to know how to use continuity correction. So what is a continuity correction? So a continuity correction factor is used when continuous probability distribution, so for our case it is normal distribution, is utilized, okay, to approximate a discrete probability distribution. So we will use continuity, okay, to approximate the Poisson and binomial. So for example, okay, for normal distribution, since it is a continuous, okay, the values can take real numbers, whereas the binomial distribution and Poisson can only be integer or discrete value. Okay, for example, here we have this value. Okay, this is a discrete. Okay, given that let's say this is the number of siblings, okay, for UTM staff and also UTM students, okay, from JB, from KL, and also from Pago. So we can see here we have number of siblings, which is 1, 2, 3, up until 11. Okay, so if we try to plot the graph, okay, of the number of siblings, and we can see that this data shows a normal distribution. Okay, and here we have the value for 1 sibling, 2 siblings, 3 siblings, and number who has 6 siblings, and so on. Okay, so how can we apply or how can we approximate this discrete, okay, where this one is just a value, right? Okay, a whole number, an integer. Okay, how can we make this into a continuous, where we need to use the normal approximation? So we can apply the normal approximation if we add or subtract, okay, from these discrete values, okay, with 0.5. Okay, so now we create a box here. Instead of just now it's just a straight line, now we have create a box where we can represent this just like a histogram graph. Okay, given that this box, for example, we know the upper and lower boundary, given that the lower boundary for this 5 is 4.5, where we minus with 0.5, and this one would be 5.5. Okay, given that 5.5 is also the lower boundary for 6, and the upper boundary would be 6.5. So now this data is no longer discrete, but okay, it's already a continuous. Okay, because for this part, okay, the lower and upper boundary is relate to each other, okay, making this as a continuous. So this is where the continuity correction needed. Okay, so this is the continuity correction factor. Okay, where it's as simple as adding or subtract 0.5 to the discrete x value. For example, here we have to find the probability of x equals to 6. Okay, so we need to do the continuity correction. So if you still remember, okay, the number of siblings, which is 6, has the highest value, right? Okay, and this is our 5 and this is 7. Okay, so there is no continuity. So we have to create a boundary here that can relate 5 with 6, 6 with 7. Okay, so there exists a continuity. So to find, okay, this lower boundary for x equals to 6, so what you can do is you have to, okay, x equals to 6, so meaning that it will be, the upper boundary would be this one and also this one. Okay, because this box represent x equals to 6, so meaning that, okay, the interval would be from 6 minus 0.5 for the lower boundary, and for the upper boundary it will be 6 plus with 0.5. Okay, next, if we need to find the probability of x less than or equals to 6, so we have to do the continuity correction first. Okay, less than or equals to 6, meaning that we have to find from 0, 1, 2 up, so up until 6, okay, which is less than x less than 6. So all of this will be in our probability 5, 4, 3, and so on. So since this box start with 6 plus 0.5, okay, the upper boundary, so after doing the continuity correction, we will find the value of x less than, okay, where 6 is included, but since the box start from this upper boundary, so it will be 6 plus 0.5. Same concept for probability of x less than 6. So do the continuity correction. So for x less than 6, meaning that 6 is not included. Okay, 6 is not included, but the rest is. So we start, okay, the boundary will start from here. Okay, where it will be from 5, okay, or 6 minus with 0.5. So this 5 will be, this interval will be included. Next is for the probability of x greater than or equals to 6. So x greater than 6, this one is 5, okay, this one is 7. So since x is greater than or equals to 6, meaning that this 6 is included. Okay, so the interval part here will not be in the interval. Okay, so P will be x greater than 6 minus 0.5. So we'll start with probability of x greater than 5.5. And when x is greater than 6, so after doing the continuity correction, where 6 is not included, so meaning that, okay, since x is not included, so we will start from 7. So here will be x greater than equals to 6 plus 0.5, which is x greater than equals to 6.5. And the last two, if we need to find the probability between 6 and 8, where 6 and 8 is not included, so this is our 6, this is our 7, and this is our 8. So between 6 and 8. So since 6 is not included, so meaning that this one will be removed and 8 is also removed. Okay, so we will start. So the interval will be at 6 plus 0.5, which is this one, and also 7, or sorry, 8 minus with 0.5. Okay, where this one would be equals to. Okay, so the probability would be from 6.5, x, and 7.5. Okay, so the last one, the probability of 6, x, and 8. Okay, all of the interval is included. Okay, so since it is included, meaning that we will start from here and here for all. So the probability would be 6 minus 0.5, it won't be included, and 8 plus with 0.5, where it will be 5.5 x and 8.5. Okay, so now try this out, okay, and I will give you the answer later. So this is the general formula for the continuous correction factor. So remember, every time you need to do the normal approximation for binomial and also for Poisson, you have to do this continuous correction factor, okay, before you solve the problem. Now let's proceed with the normal approximation of the binomial distribution. So when should we use the normal approximation for the binomial? Okay, when the number of trials n, okay, here we have n is number of trials, in a binomial is relatively large. So how large is the large? Okay, so the normal probability distribution can be used to approximate binomial probabilities. So these are the convenient rule, okay, when to use the normal approximation. Okay, so the first one is n is greater than equals to 30, and the second one is you have to check for np greater than equals to 5 and n times with 1 minus p greater than equals to 5. So if the condition, okay, follows this, satisfy these two conditions, then you can use the normal approximation. So given that our problem random variable follows binomial np, but if n is greater than equals to 30, okay, np is greater than 5 and n1 minus p is greater than 5, then x will follow normal given that your mean is obtained from np and your variance is obtained from np1 minus p. And please remember that the continuous correction factor will be used when you use the continuous probability to approximate the discrete probability distribution. So how can we use the normal approximation? So these are the steps. The first one, you have to find the P1 minus P and N because this is a binomial distribution problem. And then figure out if you can use the normal approximation to the binomial. If NP and N1 minus P are greater than 5, and also N is greater than equals to 30, then you can use the approximation. Next is to find the mean, where mean is obtained by multiply N and P. And then multiply the step 3 because here we have NP with 1 minus P to get the variance. Next is take the square root of step 4 to get the standard deviation. Okay, and then rewrite the problem using the continuity correction factor. Next is find the z-score and we get the z value in the z table. Okay, now let's do this example. Okay, in a certain countries, 45% of registered voters are male. Okay, so P is given as voters that is male. Okay, and 300 registered voters from that country are selected at random. So this is our N. Find the probability that at least 155 are males. Okay, so this is the problem of binomial. X follows binomial, given N is 300, P is 0.45. But you can see here, your N equals to 300 is greater than 30. Okay, and also let's check for NP and also for N1 minus P. So 300 times with 0.45, you will get 135, which is greater than 5. And also N times with 0.55 would be 195, which is greater than 5. So we have to use the normal approximation to solve this problem. Even if you try to solve this using the binomial, it's kind of impossible. Okay, it is time consuming. Okay, and also the value is not in the table. Okay, so now we can use the N normal approximation to get this. So given the mean is NP, okay, NP, and this one is NPQ. Right, so the normal would be NP is equals to 135 and NPQ or NP times 1 minus P is given as 74.25. So this is your mean and this is your variance. So now we want to find the probability that at least meaning that X will be greater than 155. And 155 are included, at least 155 are males. Okay, so since we use the normal approximation for this problem, first of all we need to do the continuity correction. Okay, so X is greater than 155 and 155 is included. So meaning that we will start this interval from 154.5. Okay, and this one is not included. Okay, then you have to transform this. So this is already in the normal distribution. Okay, so now you have to transform this normal distribution to standard normal. So this one would be z greater than 154.5 minus with mean. So mean is obtained from here, divide by sigma, only sigma. So the square root of 74.25. So you will get the probability of z greater than 2.26. Okay, so z greater than 2.26 would be on this side. Okay, this one is 0, so 2.26 will be here. So you need to use the table. Okay, so find 2.26 and 1 minus the area. And you will get 0.0119. Okay, so that's how you solve the binomial distribution using the normal approximation.